Okay, I'm getting a lot of glare, so I got to keep my calculator on the bottom, so I hope you can see it. Cosine of 60. Punch that into your calculator. And what do you get? 0.5? Anybody got anything else? That is a great test to make sure that your calculator is in the right mode. This is cosine of 60 degrees. It should give you 0.5. If you look at the special triangles, you'll see why. Awesome. That means my calculator is in degree mode. So if I was like starting a test in grade 11, I would punch cosine of 60 into my calculator and make sure I got 0.5 so that I know I'm in the right mode. You can also just look, there's a little D. Everybody's calculator is a little bit different, but it says D or DEG or something like that, right? And when you start doing trig in grade 10, your teacher would make a big deal making sure that your calculator is in degree mode. There's two other modes, but we only use degree mode. Well, now we're finally going to learn what one of the other modes is talking about. So find on your calculator how you would change your mode, and you want it to be in the R or the RAD mode. And now if I put in cosine of 60, I don't get 0.5. That's right. That's what we want. But I'm going to try something a little different. Cosine bracket pi divided by 3. So try to do that on your calculator. You probably need a bracket. 0.5. So now I know that I'm in the right mode for grade 12. We might switch back and forth once in a while. You might use degrees. For now, we're going to be using radians. But that would be how you could determine that you're in the right mode. Here, look for the R for radians. But there's your difference between degrees. Cosine of 60 is 0.5 radians. Cosine of pi divided by 3 is 0.5. That seems strange, doesn't it? Okay, so we're not using our calculators much just yet. You're going to use them a little bit later for some of the practice. Not too much just yet. But just so you know down the road, what mode your calculator in is going to be super important for all this trig stuff. Okay, so a little definition of what radians are. There it says, up to now, you've measured, oh, that's not turned on. You've measured angles in degrees. And by definition, a circle has 360 degrees in it. That defines the unit. That tells us what a degree is, how big it is. Because you fit 360 evenly into a circle, right? And it doesn't matter how big the circle is. You can make the circle bigger, like a bigger radius, but the degree is going to stay the same. The length to get out to the arc of the circle, the edge of the circle, will be longer, but the degree itself is always the same. Why 360? You might guess. There's no actual, we don't really know exactly why. There's 365 days in a year, so they think that probably had something to do with it. Like thousands of years ago, they probably kind of knew that it took about 360 days to go around the sun. That defined a year, so they made that a degree kind of thing. And that, but there's other reasons, like 360. These are kind of math reasons, but is divisible by a lot of things. Like think of what goes into 36. 1, 2, 3, 4, 6, 8, 9, not 8, 9, 12. Anyway, and 360's got even more things that go into it. 10, 5, both do, right? And so anyway, the point is lots of things divide into it and makes it mathematically interesting. There's also an old, really old, like group of people, the Mayans, who used a base 60 math system. So we use a base 10 math system. You get up to 10, and then you reset with a new digit in the tens place. They had 60, and then would reset. So they had a different character for the first 60 numbers. So imagine learning that, like alphabet or that number system, all the different ones. It's complicated. Anyway, and so it might have had something to do with that. Like why at 360? Anyway, they don't exactly know, but the point is, that's what defines the unit. Okay, so we're learning about radians. This is a different way of measuring angles. One of the reasons why it's really useful is that it has no unit. It is what we call unitless. Because it's a ratio, kind of like tan, sine, and cosine are ratios. Right? And it's a ratio of arc length of a segment of a circle to its radius. We'll talk about what that means in a minute. But to you, what it means is, man, this is a pain, because the first time you see it, it's often kind of complicated and seems kind of thick and seems kind of unobvious. Like, I know what a 60-degree angle is. It's really easy to know what 60 is, what 45 is, what 90 is, what 180 is. And now you just went and complicated everything. So it's a pain in high school, but for mathematicians and physicists, doing this is really, 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 really useful way of measuring angles. So mathematically, it's like really useful because it's unitless and because it has a special relationship with the circle, because it comes from the circle. But it's a little complicated at first. Okay, so what do we mean by, so you want to draw these circles. What do we mean by arc length, ratio of arc length to radius? Well, first of all, this is my arc length, okay? So I'm going to call that A. This is my radius. I'm going to call that R. Does that make sense? And so in this case, I think you can clearly tell that A is less than R. Do you agree? The arc length is less than R, and you can tell that this is kind of a smaller-ish kind of angle. And so then we would say that A over R is less than 1. The ratio of the arc length to the radius is less than 1. Just reorganize, dividing both sides by R, right? R's, we don't have to worry about negatives. This isn't an inequality thing. We're just kind of thinking here because R's radius is not negative. It's a length. Okay, what about this one? So A is this whole distance around, and there's R. R's the same. These are like the same circles. So in this case, A is quite a bit larger than R. I think you can tell that that length around the circle, it's not all the way around, but what is it? I don't know, 2/3, something like that. It's a lot longer than R. So you guessed it. In this case, the ratio of the arc length to the radius is greater than 1. If I knew what those measurements are, like I could get my ruler out and measure, well, I can't measure A exactly, but I could roughly, it's 3 centimeters. And R is 1 or something like that, right? And then think about the ratio of one to the other. Okay, it's hard to tell exactly, but it turns out in this one, whoops, getting ahead of myself here, the arc length is equal to the radius. They are equal. What kind of an angle occurs when that's true? So A over R equals 1. And that, folks, is your definition of a radian. If I think about this as A centimeters equals R centimeters, A centimeters over R centimeters, the centimeters cancel. That's what makes it unitless. And when the arc length is equal to the radius, that's when we get 1 radian by definition. I'm going to show you something. I meant to play this earlier. I forgot. So there's 1 radian, right? There's 1 arc length. And a tiny bit more, 3 and a tiny bit more. Turns out that's pi, which makes sense. It's half a circle. So 2 pi is a full circle, which we'll talk about again momentarily. So a little animation of how a radian is related to arc length and radius is where it comes from. So that's a definition of a radian. And that's what that says there. So this is worth writing down. By definition, 1 radian is when the arc length is equal to the radius, but it's a measure of an angle. Because if I make A smaller, I make the ratio smaller, I make the number of rads smaller, the number of radians smaller, and I make the angle smaller. If I make A larger, A is the numerator, so that makes the whole ratio larger, and that makes the angle, the number of radians, larger. This is not necessarily something you need to be thinking about while you're working with radians, but I think it's certainly important to know where this comes from. Every time you say, oh my gosh, why are we working with radians? It's such a pain. And like I said, it's a very convenient way of doing things mathematically. Not at first, because it seems like it overcomplicates things at first, but it turns out to be incredibly important. And then that, remember, don't forget that demonstration about the calculator. Your calculator's got to be in the right mode. 1 radian is very different from 1 degree. I can fit 360 single 1 degrees in a circle, but I cannot fit 360 radians in a circle. They're not the same thing. How many can I fit in a circle? We saw that 2 pi. We'll talk about that again momentarily. Okay, little mini formula. We'll use this a few times. We'll get to this, but again, you want to write that down. So theta, which is an angle, is equal to A over R. So if you know the arc length and you know the radius, you can find the number of radians in there. If you wanted to convert that to degrees, you'd have to do a conversion. So right away, you could, once we apply this a little bit, you can see how this is easier. It's less work in a case like this, because we don't have to convert once we understand what a radian is. If you think about a circle, half a circle is 180 degrees. So that's like 3 times 60. And for radians, we need to get 1, 2, 3, and a little bit more. So a radian is a little bit smaller than 60 degrees. It's about 57 point something. Again, that's not really, like, it gives you a frame of reference, but that's not something that we're going to use a lot. Like, you don't convert by multiplying by 57 or anything like that. Okay, so let's talk about a couple of things. For a circle, so you want to write this down for sure. For an entire circle is what we're talking about here. What would the angle be? Arc length over radius. What is the arc length of an entire circle? That's its circumference. Who knows the formula for circumference of a circle? It's like the perimeter, the length of the outside of a circle. 2 pi r. 2 pi times the radius, right? So if I sub that in, 2 pi r over r, it's the same r, it's the radius of the circle. R divided by r. And the number of radians in a circle is 2 pi. This gives us the conversion that pi radians, which is half a circle, is the same as 180 degrees. 2 pi radians. Remember, radian is the ratio of arc length to radius. So I calculated that for an entire circle. R's cancel out, and I noticed that the number of radians, theta in this case, in an entire circle is 2 pi. So that means 2 pi is the equivalent to 360 degrees. Divide by 2 on both sides. Pi is the equivalent to 180 degrees. There's our reference point. Now we know that pi in radians means 180 degrees in degrees. Does that make sense? Or are you already like, ugh, this is brutal? So if you think back, and again, once we do a little bit more of this, this will maybe be a bit clearer. But if you think back, remember we did cosine of 60 in degree mode and got 0.5. Then we changed it to radians and we did cosine of pi divided by 3. Pi divided by 3. That's the same as 60. Gave us 0.5, right? That's why we used that thing. Okay? And so then the other thing I can think of here is that pi divided by 180 is equal to 1. This is the thing, radians are unitless. It's just a ratio. So I can multiply it by anything or divide it by anything and like do all kinds of great stuff with it. So believe it or not, that's what I did right there. I took pi radians, which is half a circle, and said, well, what if I split that into 180 equal pieces? So divide by 180. Then that's going to be 1 degree. So pi divided by 180 is equivalent to 1 degree. If you can remember these reference points, then no matter what, you can always convert from one to the other. Okay, so let's go to degrees first. How do we convert 2 degrees? The easy way which is kind of skipping a step, is to replace pi with 180. So when we do that, we are actually cheating a little bit, but it's an easy way to remember how to convert 2 degrees if you had to for some reason. So for example, if I have 4 pi by 5 radians, that's a measurement of an angle. 4 pi over 5 is close to 1 pi, like that's 80% of 1, right? So you're close to 180 degrees, I guess. You're getting close to 1 whole pi. So what do? I replace pi with 180. So 4 times 180 divided by 5. And I just do that on my calculator, and it works out to 144 degrees. Doesn't matter what mode you're in at this point yet. Now, just so that we know, you don't have to write this down. You might want to, but I'm going to do it in a different color. What I actually did there is I multiplied by the ratio of degrees to radians. And then the pi's canceled, and I was left with 4 times 180. That's what we're really doing, is we're kind of using a proportion here, or a ratio. But we could cheat and replace pi with 180. Got that? Okay. Now what's more interesting, because we're going to be working with radians, is how do you go to radians? That was 2 degrees before. How do we go to radians? So for example, if I give you 130 degrees and you have to convert it to radians, so what we do is we multiply. So we multiplied by 180 over pi to go one way. So we multiply by pi over 180 to go the other direction. So 130 degrees is equal to 130 times pi over 180. which is 130 pi over 180. And then I reduce it. We always reduce. I would recommend learning how to do that on your calculator, because calculators these days are very good at that. Turns out it's 13 pi over 18. So 130 degrees is the same angle measurement as 13 pi over 18 radians. And right there, it's like, seriously, 13 pi over 18, that's the measurement system you want us to use? What a ridiculous way of representing something that was so easily done with 130 degrees. And I understand 130 degrees. It makes perfect sense. I've been using it forever. 13 pi over 18, really? That's what we're going to use? But it turns out once you get good at this, it's way better. I hope you believe me. Any questions so far? All right. We're not going to convert these with those conversion systems. We're going to think about them for a minute. If you write down all of these, these are kind of like common angles you'll see. And I'm not saying to memorize them. But going through this thinking process might help you connect to this stuff a little bit. So pi is how many degrees? 180. So what would pi by 2 be? I'm hearing people whisper it. Somebody commit themselves. What do you think? Khaled? 90. Right? It's equivalent. So yes, you divide one of them by 2, you would divide the other one by 2. Absolutely. Think of pi as 180 degrees. So what's pi by 3? We already talked about this one. 60. What's pi by 4? Well, that's like pi by 2 and then by 2 again. So that would be, Vivian? 45 degrees. That's one of the special triangles, has 45 degrees in it. So you see a pi by 4, that's what I would start thinking about. What's pi by 6? See how easy this is? 180 divided by 6, that's 30. Pi by 9? 20. Pi by 12? Calculator for this one. Or pi by 3 and then divide by another 4. Or pi by 6 and then divide by another 2. 15. That's not as common. But I like that idea. Pi by 6. I can do that easily. And then divide by another 2. All right? If your fraction skills or even just your numeracy skills are good, you can do a lot of this kind of stuff in your head. So to me, it's all about a reference point. It's knowing a few key ones of these or knowing how to figure them out and then going from there. So here's another example. So what was pi again? Oh, well, we got that 180. What's pi by 3? 60. So what's 2 pi by 3? 120, right? You have 2 times pi by 3. So 120 degrees. I didn't need to use a formula for that. I didn't need to replace pi with 180 and multiply through. I just think about, well, pi over 3 is 60. I have 2 of those is 120. So what's 4 pi by 3? 240? Five pi by 3. So I've got 5 60-degree angles. Go back to the pi by 3, that's 60. I've got 5 of those, so that's 300. All right, let's see if we can do this. So pi is 180, pi by 2, half that. And then take 3 of those, and that's 270. Okay, let's see if you can start filling out this list a little bit. You can use a calculator. Like, I'm not trying to say no calculators allowed or anything like that, but so pi by 4 is 45. So if I have 3 of those, 90 is 2 of them. Other 45, 135. Five pi by 4. Well, I can think of this as lots of different ways, right? Like everybody can make their own connection to it, but that's like 4 pi by 4, which is 180. That's a whole pi, plus another quarter. So 180 plus another 45. Is that 225? 7 pi by 4. Maybe you get your calculator out for this one. Well, pi by 4 is 45. So what's 7 times 45? Give me that one. 315. Or I could even think of it as like this is where angle's in standard position. 360 all the way around minus the quarter to fill it up. Like 2 pi is a full circle. So that would be 8 over 4 would give you 2 pi. You got 1 less than that, 145 less than that. Lots of different ways to think about this. Any questions about any of that? All right, let's try a few. We already did 120 above, I believe, but we're going to do this the computational way. So how do we do this one? 120. I'm converting 2 radians. So I multiply by pi and divide by 80. So this is 120 pi over 180. And then use your calculator, or if you think you can do that in your head. I mean, some of them are easy. 120 is 2/3 of 180. Or, like I said, use your calculator, and you get 2 pi by 3. Okay, try the next one. When you're doing this on your calculator, don't put the pi in there, right? We're trying to get exact values. Sometimes you get a decimal value. Like once in a while, if we're applying it, we care what the decimal is, but often we want the exact value. So don't put pi in your calculator. I just put 120 over 180, hit equals. Okay, so what's this next one? 250 pi over 180. 250 is bigger than 180. That's like in quadrant 3. Like again, you can start connecting this to the quadrants, which are the quarters, 90, 180, 270 to 360, right? Kind of that's what eventually you want to feel as connected to radians, maybe not quite as, but as you do degrees, so that when you think about an angle, 5 pi by 4, well, what is that? Like, what quadrant is that in? So 250. So this just works out to, I believe, 25 pi over 18. Okay. Try these. So again, we've already done this one several times, but let's see it in action here. So how do we do these? I just replace pi with 180. 2 times 180 divided by 3 on my calculator. Okay, and you can try the next couple. $540, so that's more than a circle, because a circle is 2 pi, so 3 pi is going to be more than a circle, 360 plus another 180, right? So whenever I'm doing these, I'm starting to try to make connections with those reference points. Everybody okay so far? Any questions? Okay, a couple of different kinds of questions. These are, I think, pretty easy, but like just getting us to think about them in a different way. Determine the angle made by an arc length of 5 centimeters in a circle with a radius of 8 centimeters. So if that's 8, 5 is smaller than that. Remember our little formula? A over R, that's all there is to this. So that's 5 centimeters divided by 8 centimeters. Again, we don't have to do the centimeters part every time, but just to remind us that that's why it's unitless, because it's a ratio, because the centimeters cancel out. There's no pi in that. So 5 divided by 8 is 0.625, depending on how it wants you to answer this. What does that mean? 0.265 of 1 rad, right? And how would I convert that to degrees? Multiply by 180 over pi, if you had to. If the question said that, you know, so if there is no pi in the question, right? Remember up here, like it's easy to just replace 180 with pi, but if there's no pi in the question, remember what we're actually doing is multiplying by 180 over pi, and the pi's cancel. So if you can't do that for some reason, then you just go back to the fundamental things. Okay, determine the arc length made by an angle of 60 degrees in a circle with a radius of 9 meters. So there's 9 meters. That's about 60, hopefully. Find arc length. Well, first of all, our formula of arc length to radius is in radians. So we got to convert 60, which is pi by 3. Remember, 180 divided by 3 is 60, same thing. Equals A over 9. Multiply both sides by 9, and I get 9 pi over 3 equals A. And A equals 3 pi, which is approximately 9.42 meters. We were finding a length there. We weren't finding that length is just over the radius. Remember I said 1 radian is like 57. So if it's 60 degrees, it's going to be just a little bit more. Makes sense. Any questions? Okay, so we're going to do an angular velocity question. These are all a little bit different. The textbook, this section of the textbook does have an example, and they talk about using a formula. So if that makes sense to you, you can do that. I'm going to use proportions because I like proportions. They work in so many different areas, not just these kinds of problems. And you kind of build your own formula as you go. So what we have here is a vat. That's like a big tank. And it has a 2-meter long arm that's rotating and stirring whatever chemical is in the tank. And that arm rotates around 3 times in 1 minute. So because this is asking for radians per second, what I want to find out is how many times or how many seconds does it take to go around once if it takes 60 seconds to go around 3 times. And if I say that little sentence in my head, thinking about the units on top and the units on bottom, so this is seconds on top, and this is number of rotations on the bottom, okay, then I can get sort of the unit rotation for this. So it's going to be helpful. So you end up just dividing 60 by 3, and that makes sense. If it goes around 3 times in 1 minute, then it takes 20 seconds to go around 1 time. Now, that makes sense, but proportion will always get that for us. And so it's taking 20 seconds to go around the circle once. How many radians is once? Okay, so we're looking for how many radians per second. We know it goes around 1 full rotation in 20 seconds. So again, we can set up a proportion, right? So how many, in the angular velocity, we use a scripted W. I'm just going to use a normal W. How many radians in 1 second? We know that a full circle is 2 pi radians in 20 seconds, right? So W, how many radians in 1 second? So that's going to be radians per second. That's our units. If I can go 2 pi, a full circle, that's how many radians are in a full circle in 20 seconds. So you can see now how it was effective to find out how many seconds it took to go one rotation. So now I can do 2 pi over 20 is pi over 10. That would be my exact value. And then if I can find my calculator, let's see, pi divided by 10, well, obviously that's going to be 0.314159265, so on. And that is angular velocity, so that's radians per second. Okay, so that's question A. Question B, how far does the tip of the arm travel in 3 minutes? So, I mean, I could use the angular velocity to figure that out, but I would still have to do some conversions because now it's asking for 3 minutes. So that's easy. That's 180 seconds. But the radians per second, I would have to turn that into like distance per second. So I'd have to take in the 2 meters and figure out the distance. So, I mean, that would be a fine way of doing it. But I can kind of set up proportions and just do this again that way. So 2 meter long arm goes around 3 times in 1 minute. So that's going to be, it's going to travel 9 times around in 3 minutes, right? And I mean that, again, I don't really need to. How many times in 3 minutes? If it goes 3 times in 1 minute, multiply both sides by 3, x equals 9. So 9 rotations. So next what I want to do is figure out, let's say, the distance that it travels once around. So that's just the circumference, which is 2 pi times the radius. But the radius is 2 meters. So that's 4 pi meters, which is a number, 12 point something, 4 times 3.14, 4 times pi, 12 point something. But I'll leave it as 4 pi for now. Okay? And so if one rotation is 4 pi, but it goes 9 rotations, then my distance is equal to 9 times 4 pi, which is 36 pi. And of course, if I was asked for this in some kind of meaningful measurement, let's say 313.1 meters is how far it would travel in 3 minutes. But every question, like I said, is a little bit different, so you can't necessarily do them exactly like this. But you're thinking about circumference, how far it travels in one revolution, how many revolutions it takes, possibly how many revolutions per second or radians per second. There's a lot of different measurements in units and things that you could calculate here, and every question is a little bit different. So think about the distance using circumference and think about proportions. And if you can set those up, then you can probably solve any of them.